Hello, everybody. Today we are going to discuss the research on deep residual neural network conducted by these people. I'm not going to try pronouncing the names because I know there will be some major mispronunciation. Now, butcher the name it will be disrespectful, and I don't want to do that. So let's just talk about the topic. Entire research is summarized in the article FPGA accelerates deep residual learning for image recognition. Research paper itself is well organized and professionally written, and idea of using FPGA for residual neural network is a real creative idea for an experiment. However, I believe that while concept sounds cool in theory, the idea will not work in practice. I promise I will explain my reasoning, but to understand why FPGA is not suitable for residual neural network, we have to first understand what residual neural network is. And to understand what residual neural network is, we need to have some idea about what neural network is itself. Now, if you have any knowledge about machine learning or any experience, you probably already guessed what I'm going to talk about. You already know what I'm going to talk about, and you probably guessed why this will probably not work. And good job. But if you don't have any idea, don't worry. I'm going to try to explain everything. And if you're interested in the subject, there are tons of sources in the internet, and you can learn it yourself. It's a very interesting topic, by the way. So, what are neural networks? Let's start with the example. Uh, what number do you see? Now, if your answer was 7, good job. You're probably master of recognizing numbers. But if I show this image to a computer, it wouldn't be able to understand what this ugly symbol is, right? Computers can't recognize handwritten symbols. That's exactly what neural networks are for. See, neural networks can actually recognize these sort of things. For example, LeNet, which is one of the most popular and also simplest neural networks, does exactly that. It recognizes handwritten stuff. But how does these machines do that? It's supposed to be impossible, right? Well, no, not at all. I'm not going to try to pretend that understanding how neural networks work is the easiest thing there is, but it isn't that hard either. Once you start learning this subject from persons that is much more qualified than I am, you will find that understanding neural networks is about as hard as solving a single problem in calculus or linear algebra, which it definitely is not the hardest thing in the world. Let's start to understand how these things actually work. Let's try this hypothetical model. When our square in which we write these numbers, handwritten numbers, has width and height of 10 pixels. And now, look, right from the start, I want to make this clear. This is garbage. 10x10 pixels is too low resolution to write anything, and it's obviously not going to work. It's also, if you look model of my neural network, it's too simple. It has like 2 layers only, 2 hidden layers, and 100 inputs. So it probably won't be able to recognize any number outright. But for theoretical purposes, to understand how this works, let's just say, let's just take this example. So as you can see, this 100 numbers, if you already guess, was 10x10 pixels represented in one dimension. And well, what these 2 layers do and how this works. Actually, it's not that complicated, but it's kind of complicated. If we do more math, it's easier to understand. These 100 pixels each has, well, each circle here is called neuron, and every single neuron has some numerical value that is number between 0 and 1, and this number represents color of the pixel. For example, 1.00 will be white and 0.00 will be black. Any other number will be some shade of gray between black and white accordingly. So now these numbers, like numerical value of neuron, is taken as an input by a function, and this function in our case has 16 outputs, or we can say a vector of lengths of 16. Then these 16, again, same process repeats. These 16 numbers are taken as input in function that has 16 outputs in our case, and then another 16 inputs are taken to give output of 10 numbers. And how does this work? Well, out of these 10 numbers that we will have as final output, each one of them will have some numerical values, and in ideal case only one of them should have a value of 1, and every single other should have a value of 0. If we like have this input 9, then 9/10th output should have value 1.00, and every other from 0 to 8 should have numerical value of 0.00, which means that computer thinks that number written by me was 100% 9 and 0% any other number. What does that math look like? What's the function? Well, I'll try to explain it shortly. The function is actually each neuron has its own weight for each output. So for one out of 16 outputs in first case, there are 100 inputs, right? There are 100 weights for first output, another 100 weight for second output, and so on and so on. So this brings for first case like 1600 weights, and then weighted sum is found, and some bias number is added, and after all of that, we take sigma function of given number, and that brings down output from 0 to 1, and that's how it's done. And well, problem then becomes what are weights, what are values of weight, and what are values of bias number. Well, that nobody knows for sure. That's just they use method of backpropagation, which is they just input random numbers as weights and bias numbers, and what they do is that they use these random numbers to give false answers, and then give correct answers as inputs, outputs, and just neural network itself finds correct value of weights and bias numbers. It's more complicated than obviously. There is like some linear algebra and calculus involved. Like, for example, how does neural network find itself correct value of weight and bias number? Well, it's using gradient descent, but it's just too complicated and we don't have time for that, and also we don't need to know that to understand what's going on here. So let's just move on. And this is LINET. LINET is one of the easiest neural networks. It's kind of different. If you see structure here, it's kind of different from what I showed in previous slide, but working principle is exactly the same. It's just some convolution and some sublink layers added, and LINET can recognize numbers and symbols pretty accurately. But with that being said, that's not actually what neural networks are used for. Like recognizing hand-rendered numbers, that's not what they are used for. And then the question becomes, what are they used for? Well, a neural network has mostly one job to do, and that's to recognize image. And well, what does that mean? It means that if you input image of a dog, for example, it should be able to tell you that it is a dog. It will also probably tell you what kind of dog it is, like if it is pit bull or husky. And that's what neural network like AlexNet does. AlexNet is much more complicated than LINET. As you can see, it has 34 layers, and it recognizes images pretty accurately. And this is what AlexNet actually looks like. Now, this is much bigger than LINET was. Actually, correct term would be much deeper than LINET was. But AlexNet is not actually the deepest neural network there is. And that brings us to residual neural networks, also called ResNets. ResNet was created first in 2015 and was revolutionary idea at the time because of one simple change. See, when neural networks such as AlexNet and others use different layers for convolution and some sampling, they inevitably lose some part of the information on the picture. To solve this problem, ResNet started using skips. Now, what does the skips do? Glad you asked. Main idea was that if input for one layer is information given by a previous layer, what if we add to that input the original input, which still has every bit of information present? Well, each input already includes information from previous layer, and adding more information from all other previous layers will not have negative effect by any means, right? Like previous information from previous layer is already there, it will already be converted on some sampling. So this skipping element will only make things better. It will not make worse by any means, right? Well, they tested their theory and it actually worked. Now this is comparison between AlexNet and ResNet, and you can see how the skipping element works. Like information is added from layer, but also from layers, couple layers ago. And when AlexNet was compared, we can see that ResNet was much more accurate. Like if we if we compare layers, level of accuracy was not that different. It was just marginal improvement. But if we compare 34 layer AlexNet and 34 layer ResNet, ResNet has significant improvement, like more than 3%. Also, if we look at plain neural network or AlexNet, we can see that growing number, like increasing number of layers, actually has negative effect, and it makes it makes neural network less accurate. But in case of ResNet, adding more layers made it more accurate, and because of that, creators had another brilliant idea. They need to go deeper. Now, if other neural networks again use too many layers, they cannot be as accurate as they were. And the reason for that is that there is actually not enough space for components in memory. There's not enough space, so they don't work as good as they are supposed to work. They're not as accurate as they're supposed to be. But because of skipping elements, ResNets do not have this. ResNets do not have this problem because they don't have that much components as other neural networks. So they can add more layers, and they will not be as big as other networks are. So they can still fit in the same place with more layers. And as you can see, being deepest network there, like ResNet is deepest network, and they started adding even more layers, and from 34 it went to 50, then it went to 101, and then we had ResNet 152. Actually, this picture is not of ResNet 152, it's ResNet 50, and we imagine ResNet 152 is probably 3 times bigger than that. That's how deep it is. And it improved accuracy, and ResNet 152 actually won 2015 ImageNet contest with accuracy of 3.57, top 5% error. This means that when picture was given and ResNet tried to analyze it, at 3.57% of the time, it was not top 5 answer of the picture. Other than that, it got it always right, and that's pretty amazing. Now, They also continued to go deeper than that, and they actually had resonate to 1202, but it was not as successful as also resonate. Like, it was less accurate than resonate 110. And reason for that is that 1202, resonate 1202 actually had too much parameters. Like, if we look at the graph here, it had 19.4 million, and it's much more parameters than other resonates, and even more than, like, 10 times more than other plane networks had. So while it was still very, very accurate, it was not as accurate as resonate is supposed to be. So it was kind of failed experiment, but the reason for that, as we know, is too much parameters and too much components coming with too much layers. And that brings us to our paper. Now, obviously, the question is, how can we improve? How can FPGA improve resonate? There are two ways to improve it. First is to increase the accuracy, and second is to increase speed. Obviously, FPGA can't do anything about network accuracy, but it can theoretically increase speed, and that is exactly what this experiment was trying to achieve. They pretty much said it in their goals. Like, they actually said in their goals that they are trying to improve speed, not accuracy. It was the goal to remain as accurate as it previously was, but goal was not to improve accuracy, it was to improve speed. Do I believe that performance speed was improved? Yes, I do. They bring several sources which, along with theoretical explanation, makes me believe that speed of neural network on FPGA is higher than its speed on CPU or GPU. However, I also think that accuracy will suffer. They even mentioned in an article that FPGA doesn't have that big of a memory, and that will be a problem. Maybe it wouldn't be a big of a problem for plain neural network like AlexNet, but for ResNet it is a big problem. The thing that makes ResNet so accurate is introducing skipping element. And if after skipped input, like if skipped input doesn't have enough space and some information is lost, the whole point of skipping is lost as well. That's why I think experiment didn't work, and accuracy of network on FPGA was much lower than it normally is. Wait, hold on. Wait, what? 92.3% top 1 accuracy and 99.6% top 5 accuracy. This is just accurate as regular ResNet. But why? Didn't I just say that actually it should be lower and it shouldn't be that accurate? Like, did I make a mistake? Or maybe they lied. Maybe they lied in the article. What's going on? Well, actually, I have explanation, and no, explanation is not that I made a mistake, and obviously they didn't lie in research paper. Trust is much simpler than that. See, if we compare this error percentage to ResNet 152, error percent in 2015 is much higher than one we had in this research, and that should be impossible, right? Because it wasn't even goal of this research to increase accuracy, and FPGA can't do anything about accuracy. So its goal was to increase speed. Why does this research has higher percentage of accuracy than in 2015 a revolutionary ResNet had? Revolutionary ResNet 152 had in 2015. Well, what I think is going on is that these results in a book were actually not test results, but training percentages. And training error percentages are always lower than actual test error is. I believe tests are run on these FPGAs, they wouldn't see that they weren't as accurate as regular ResNets are. But why? Well, it's kind of similar to what happened to ResNet 1202, ResNet 1202 was just as accurate as ResNet 110 was, and that was during training. There was they almost never made mistakes, but when they were tested, actually ResNet 110 was significant ResNet 110, and the reason for that is that ResNet 110 was more accurate than ResNet 12. For that is that when this theory is tested in practice, there is not enough space for that many components and that many parameters. And when there's not enough space for that many parameters, accuracy starts to drop. And that will happen with ResNet 1202, and that's probably what will happen with FPGA, even if ResNet is not, that doesn't have that much layers. Like FPGA, when we're testing ResNet on FPGA, even if we have ResNet 150 or 152 or 50 or 101 or 110, that doesn't mean too much layers and too much parameters. It will be just regular ResNet, but it does mean that we are doing this on FPGA, which has less space and less memory. So it will have same effect, and that's why I think when this theory is tested in practice, and not just training percentages are given, I think this will probably be worse. Top 5 will not be, definitely will not be 99.6. It will probably be something more towards 95% maybe, or not even that, 90%. And well, top 1 results will suffer even more. So that's it for today's video, and I'm sure you didn't understand much I said, but if you look deeper and read articles, you'll probably be able to understand why this research is probably mistaken and will not result in anything new and revolutionary. Thank you for listening, and goodbye.